In the unforgiving calculus of aerial warfare, every bolt, every composite panel, and every line of code can dictate the razor-thin margin between victory and oblivion. It is a domain where technological surprise is the ultimate currency, and for decades, the West has held a near monopoly on its minting. That era ended definitively in the waning days of December 2024. As the world turned its attention to festive celebrations, a new specter materialized in the cold, hazy skies over Shenyang, the heart of one of China's premier aerospace industrial complexes. Grainy photographs and fleeting video clips, disseminated with calculated imprecision across social media, captured a shape both alien and yet strangely familiar. A twin-engine, tailless combat aircraft that bore no resemblance to anything in the known inventory of the People's Liberation Army Air Force. This was not a leak, it was a proclamation. The aircraft, tentatively designated J-50 or JXDS by a global community of analysts scrambling to make sense of the apparition, was the physical embodiment of a generational leap. Its maiden flight, believed to have occurred in secret around December 20th, was followed by this carefully managed public debut on December 26th, a date that coincided with the nearly simultaneous appearance of an even larger, more enigmatic prototype from the rival Chengdu Aircraft Corporation, the J-36. The coordinated unveiling of two distinct sixth-generation platforms was an act of profound strategic messaging, a clear signal that Beijing was no longer merely a participant in the race for air dominance, but was now setting the pace, fielding tangible hardware, while its Western counterparts were still debating program costs and refining PowerPoint presentations. The J-50, trailed by a Shenyang J-16 strike fighter acting as a chase plane, was not just a prototype, it was a challenge cast in titanium and carbon fiber, a declaration that the future of air power would be contested in ways previously unimaginable. To understand the significance of this new silhouette, one must deconstruct its form, for its anatomy reveals its intended function with brutal clarity. The J-50 presents a masterclass in modern, low-observable design, yet it is a design that makes deliberate and telling compromises. The forward fuselage is dominated by a long, broad, diamond-shaped nose radome, its geometry suggesting the presence of a very large and powerful active electronically scanned array, AESA, radar. This section is divided by a prominent chiny line that blends seamlessly into the rest of the airframe, a feature designed to manage radar reflections and improve aerodynamic performance at high angles of attack. Above this sits a streamlined, blended bubble canopy, which, after initial speculation fueled by the low-resolution imagery, was confirmed in subsequent sightings in early 2025 to house a single pilot. This put to rest theories of an uncrewed or optionally crewed platform, indicating that for this particular role, the PLAF still values a human decision-maker in the cockpit. Below the fuselage, the design lineage from previous Chinese stealth programs is evident. The aircraft is fed by a pair of V-shaped ventral air intakes that employ a diverterless supersonic inlet, DSI design. This feature, a hallmark of both the Chengdu J-20 and the Shenyang J-35, eliminates the need for heavy, complex, and radar-reflective mechanical intake ramps by using a carefully sculpted bump to manage boundary layer airflow, a solution that is both elegant and critical for maintaining a low radar cross-section. The main body of the aircraft is a blended wing-body configuration, maximizing internal volume and aerodynamic efficiency. Visible on the underbelly are two separate ventral weapons bays with a distinct centerline tunnel indented between them, a configuration optimized for carrying a mix of air-to-air munitions internally to preserve its stealth characteristics. The aircraft rests on a tricycle landing gear arrangement, but it is the nose gear that offers one of the most significant clues to its ultimate purpose. Unlike a typical land-based fighter, the J-50 is equipped with a heavy-duty, twin-wheeled nose landing gear. This is a design feature almost exclusively associated with carrier-borne aircraft, engineered to withstand the tremendous structural stresses of catapult launches and arrested recoveries. Given that its manufacturer, Shenyang Aircraft Corporation, is the primary developer of China's naval fighters, from the Su-27-derived J-15 to the new fifth-generation J-35, this is no coincidence. It strongly suggests that from its very inception, the J-50 was conceived with a naval variant in mind, intended to operate from the decks of China's growing fleet of catapult-equipped aircraft carriers. It represents a long-term vision to leapfrog the F-35C generation and field a true sixth-generation platform at sea, directly challenging the U.S. Navy's own F/A-XX future fighter program. The airframe itself is undoubtedly constructed from a high percentage of advanced composite materials. Following the developmental trajectory of the J-20 and J-35, which saw an increasing reliance on carbon fiber composites, metamaterials, and sophisticated radar-absorbent coatings, the J-50's smooth, seamless skin and precise panel alignment point to a mastery of manufacturing tolerances essential for very low observable platforms. This is not merely about weight reduction, it is about creating a structure that is both strong enough for extreme maneuvering and electromagnetically tailored to absorb and deflect radar waves across multiple frequency bands. Where the J-50 transitions from an evolution of existing stealth principles to a revolution in aeronautical engineering is in its flight control philosophy. The aircraft is radically tailless, completely dispensing with vertical stabilizers. This is the holy grail of wideband stealth, as vertical tails are a primary source of radar reflection, particularly from side and rear aspects. However, eliminating them creates a platform that is inherently unstable in the yaw axis, prone to uncontrolled side-to-side oscillations. The solution engineered by Shenyang is both audacious and breathtakingly complex. The aircraft's primary lifting surface is a cranked arrow or lambda wing. This unique plan form combines a sharply swept inner wing section, optimized for low drag during supersonic flight, with a more moderately swept outer section that improves low-speed handling and generates more lift for maneuverability. This design provides a superb balance across the flight envelope and creates significant internal volume for fuel, extending the aircraft's combat radius. But the true genius, or madness, depending on one's perspective as a flight control engineer, lies at the wingtips. The J-50 features large, actuated, swivelable wingtips that can move independently of each other. Photographs from test flights have captured the aircraft with its starboard wingtip drooped down while the port tip remained level, confirming that these are not mere flaps, but primary multi-axis control surfaces. They are designed to function as ailerons for roll, elevators for pitch, in conjunction with trailing edge flaps, and most critically, as rudders for yaw control through differential deflection. This configuration is augmented by lengthy differential leading edge extensions, LEXs, and, as will be discussed, two-dimensional thrust vectoring from its engines. The sheer computational challenge of making this system work is staggering. The J-50 is an aircraft that is physically impossible to fly without an exceptionally advanced, multi-redundant, and likely AI-assisted fly-by-wire flight control system. This is a design so inherently unstable that its flight control software must be less a product of conventional coding and more a result of a Faustian bargain with the laws of aerodynamics, requiring a dedicated team of computational demonologists to ensure the aircraft doesn't simply decide to fly apart in a fit of pique. The software is no longer just a system on the aircraft, it is the aircraft. This elevation of control law algorithms to a primary structural component demonstrates a level of confidence and mastery in this field that places China's aerospace industry squarely at the forefront of global development, creating a platform whose agility could potentially exceed anything currently flying. At the heart of this revolutionary airframe are its two engines, the source of its power and a key element of its signature management strategy. The J-50 is a twin-engine design with its power plants housed in bays situated at the rear of the blended fuselage. The most revealing feature of the propulsion system is the design of its exhaust nozzles. The prototypes have been consistently observed with two-dimensional, 2D thrust vectoring nozzles, similar in concept to those on the American F-22 Raptor. These rectangular nozzles can deflect their thrust up and down, providing powerful pitch control authority that is essential for compensating for the lack of traditional horizontal tail stabilizers and enabling extreme maneuvers. The edges of these nozzles are serrated in a sawtooth pattern, a common technique used to scatter radar waves and reduce the aircraft's detectability from the rear. However, observations of different prototypes throughout 2025 have shown variations in nozzle design, with some appearing more circular and others more distinctly rectangular. This suggests an ongoing and intensive phase of experimentation, likely focused on developing and integrating a next-generation engine. The global consensus is that true sixth-generation performance, particularly the ability to supercruise or maintain supersonic speeds without the use of fuel-inefficient afterburners, requires an advanced variable cycle engine. These adaptive power plants can alter their bypass ratio on the fly, functioning like a high-thrust turbojet for combat situations and a high-efficiency turbofan for long-range cruise. This capability not only dramatically increases range and persistence, but is also central to advanced signature management. By optimizing its thermal cycle, an adaptive engine can significantly reduce the aircraft's infrared signature, making it harder to detect and track by enemy heat-seeking sensors. The J-50's low-drag, tailless design is aerodynamically predisposed to supercruise, and even with current-generation engines like the WS-10C, it would likely possess significant supersonic cruise capabilities. But the experimentation with nozzle shapes points to a more ambitious goal: the perfection of a propulsion system that manages its signature across the entire electromagnetic spectrum. The serrated 2D nozzles address radar returns, while the thermal management inherent in a future variable cycle engine would address the infrared spectrum. This holistic approach to stealth, treating it as a multi-layered problem of managing radar, infrared, and even acoustic signatures, marks a mature design philosophy that aims to make the J-50 a truly elusive and survivable platform in the most contested environments. Beyond its physical form, the J-50 is fundamentally designed to be a dominant node in a networked battlespace. Its primary role may not be simply to launch weapons, but to see, process, and share information on a scale that overwhelms an adversary. The aircraft's sensor suite, as far as can be determined from open-source imagery, is formidable. A chin-mounted turret housing an electro-optical targeting system, EOTS, is clearly visible under the nose, providing passive, long-range detection and tracking of targets without emitting a radar signal. This is complemented by a series of small, dark panels and subtle bulges around the airframe, particularly behind the cockpit, which are strong indicators of a distributed aperture system, DAS. DAS uses multiple infrared sensors to create a seamless 360-degree spherical image around the aircraft, allowing the pilot to see through the airframe, providing unparalleled situational awareness, detecting missile launches from any direction, and tracking multiple aircraft simultaneously. This passive sensor data is fused with the information from its large AESA radar and inputs from off-board platforms through high bandwidth, low probability of intercept data links. This is the core of the system of systems approach that defines sixth-generation thinking. The J-50 is not intended to fight alone. It is conceived as the quarterback for a team of manned and unmanned assets. Its combination of extreme survivability, thanks to its multi-spectrum stealth and its powerful integrated sensor suite, makes it the ideal platform to penetrate deep into enemy airspace, absorb vast amounts of battlefield data, and build a high-fidelity, real-time picture of the tactical environment. Its onboard processors, likely leveraging artificial intelligence and machine learning, will then fuse this data into actionable intelligence, not just for its own pilot, but for the entire network. The J-50 becomes a flying brain, a forward-deployed command and control node that directs the actions of swarms of less expensive, attritable, unmanned, loyal wingman drones, or collaborative combat aircraft, CCAs. These CCAs can act as sensor mules, weapons trucks carrying additional missiles, or dedicated electronic warfare platforms. This doctrine fundamentally alters the strategic and economic calculus of air combat. An adversary is no longer faced with the task of defeating a single high-value fighter. They must contend with an entire distributed, resilient, and intelligent network commanded by it. The J-50's value is thus magnified, measured not by the weapons it carries in its own bays, but by the collective combat power of the swarm it directs. Ultimately, an aircraft is defined by the instruments of power it brings to bear, and the J-50's design points toward a very specific and lethal purpose. Its two ventral weapons bays are sized to carry China's next generation of air-to-air missiles, AAMs. While it can certainly employ existing munitions like the long-range PL-15, its design is likely optimized for weapons such as the PL-21. The PL-21 is a ramjet-powered, very long-range AAM with a range estimated to be well over 300 kilometers. Unlike a traditional rocket-powered missile that burns out and coasts, a ramjet engine breathes air and can maintain power throughout its flight, meaning it arrives at its target with tremendous speed and energy, making it exceptionally difficult to evade. Equipped with its own AESA seeker and advanced electronic countermeasures, the PL-21 is a weapon designed specifically to engage and destroy high-performance, agile, stealthy targets at beyond visual range, BVR. This weapon, combined with the J-50's airframe, clarifies its operational doctrine. The PLA-F's existing J-20 is a heavy, long-range interceptor, more focused on BVR engagements and precision strikes than on close-in maneuvering. It is China's analog to the F-22, but with a greater emphasis on range and payload over pure agility. The even larger J-36 is almost certainly a tactical or regional bomber, a penetrating strike platform. This creates a distinct doctrinal gap for a dedicated air superiority fighter, a machine built for the singular purpose of clearing the skies of enemy aircraft. The J-50 fills this role perfectly. It is smaller and more agile than its sixth-generation stablemate, the J-36, and its design philosophy represents a deliberate balance between stealth and extreme kinematic performance. It is a purpose-built Raptor hunter, engineered from the ground up to seek out and destroy the West's most advanced fifth-generation fighters. The intended combat sequence is clear. Use its superior stealth and fused sensor data to achieve the first look. Launch a high-energy PL-21 from BVR to neutralize the threat. And, should the engagement merge to within visual range, employ its revolutionary flight control system, the combination of a tailless design, articulating wingtips, and thrust vectoring to dominate the dogfight. It is a complete weapon system, a duelist's rapier to the J-36's broadsword, designed to ensure that in any future conflict, the PLAF controls the vertical dimension. Placing the J-50 within the global landscape of next-generation fighter development reveals both convergent trends and fascinating philosophical divergences. Every major power is pursuing a system of systems approach, recognizing that the future of air combat lies in networked platforms. The United States Next Generation Air Dominance (NGAD) program is centered on a penetrating, long-range crewed fighter, now designated the F-47, operating in concert with a family of CCAs with a clear focus on addressing the vast distances of the Indo-Pacific theater. In Europe, two competing programs are underway. The Franco-German-Spanish Future Combat Air System, FCAS, is a similarly ambitious system of systems concept, but its development has been marked by industrial disputes and a more protracted timeline aiming for a 2040 service entry. The Trilateral Global Combat Air Program, GCIP, uniting the United Kingdom, Italy, and Japan, merges the former Tempest and FX programs into a single effort with a more aggressive 2035 target. Both European efforts and the American NGAD appear to be trending towards large, long-range, and very expensive crewed platforms designed primarily for BVR combat and deep strike missions. China, however, is pursuing a distinct dual-track strategy. The tandem appearance of the J-36 and J-50 demonstrates that it is developing both a large NGAD-style penetrating strike and command platform and a smaller, hyper-agile air superiority fighter. This suggests that while the West may be designing its future air forces around the assumption that BVR combat will be decisive and that close-in engagements are to be avoided, China is preparing for both contingencies. It is building a force structure where the J-36 can prosecute long-range strikes and orchestrate the networked battle, while the J-50 can penetrate contested airspace to achieve local air dominance, protecting those higher-value assets and ensuring their freedom of action. This two-pronged approach presents a far more complex tactical dilemma for an adversary, forcing them to counter both a standoff BVR threat and a lethal close-range knife fighter. The J-50 is a stark reminder that in Beijing's vision of the future, the age of the dogfight is not over. It is being reinvented with a level of technological sophistication that may leave its rivals unprepared for the ferocity of the coming fight. The specter over Shenyang has cast a long shadow, and the great game in the skies has been irrevocably changed.